May 9, 1876, Philadelphia, Pennsylvania. The engineering report from the Centennial Exhibition's mechanical jury would never fully capture what they witnessed that afternoon. A German inventor demonstrating an engine using principles that defied everything steam power tradition said was necessary for reliable industrial operation. Through the noise and machinery of the exhibition hall, a peculiar four-stroke engine operated with efficiency that seemed impossible to experienced engineers. No massive boilers, no continuous combustion, no proven reliability from decades of steam tradition. Yet it ran with fuel economy that conventional steam engines could not approach. In British factories, master engineers required enormous facilities to generate reliable power using steam technology perfected through generations. Each installation demanded constant coal feeding, water supplies, and maintenance crews. Power output remained impressive, but fuel consumption created operating costs that limited profitability. Most industrial leaders accepted these limitations as the unavoidable price of mechanization. The Germans were operating with a combustion philosophy the British had never imagined practical. 4 distinct strokes, intermittent combustion, precise valve timing, fuel efficiency that transformed engines from massive installations to portable power sources. 900 miles from British factories, the most decisive mechanical revolution in industrial history was revealing itself, not in superior tradition, not in craftsman intuition, but in the systematic combustion control that connected every rotation of Otto's engine in ways steam engineers never imagined possible. Industrial Germany carved through the heart of Europe like a nation desperate for mechanical independence. By 1870, German manufacturers watched helplessly as British steam technology dominated continental factories through sheer power, output, and proven reliability. Every month brought fresh reports of German workshops purchasing British equipment drawn by steam engines that could deliver horsepower exceeding anything German inventors had developed. The numbers told the story with brutal clarity. German industrial output lagged 30% behind British production, while coal consumption doubled annually without proportional increases in manufacturing capacity. Germany's engineering community understood they faced permanent technological subordination unless they could solve a fundamental problem that had defeated every alternative to steam power for decades. No internal combustion engine operated reliably enough for factory use. Experimental gas engines consumed fuel erratically, delivered inconsistent power, and broke down frequently under sustained industrial loading. The nation's inventors knew they had one desperate chance to challenge British steam dominance. Perfect an engine that could match steam's reliability while eliminating the massive infrastructure that made steam power expensive and inflexible. Nicolaus Otto received support through a combination of German national pride and technical insights that seasoned engineers considered theoretically interesting but practically worthless. The 53-year-old inventor had studied every failed gas engine design, learning from mistakes that had convinced most engineers that internal combustion would never replace external combustion systems. His experience working with atmospheric engines had taught him that combustion timing and compression ratios held secrets that previous inventors had never understood properly. But Otto possessed something his steam-committed competitors lacked: absolute certainty that the future belonged to engines that carried their fuel rather than dragging coal cars and water tanks behind them. Otto's design proposal shocked the mechanical establishment. 4 separate strokes, each serving a distinct function in converting fuel energy to mechanical power, operating in a sequence that seemed unnecessarily complicated compared to steam's continuous combustion. The intake stroke would draw fuel and air into the cylinder through carefully timed valve operation. The compression stroke would squeeze this mixture to pressures that previous engines had never attempted, creating conditions for efficient combustion. The power stroke would harness expanding gases to drive the piston downward with force exceeding steam engine performance per unit of fuel consumed. The exhaust stroke would expel spent gases, preparing the cylinder for another cycle. British-trained engineers declared the proposal mechanically overcomplicated and thermodynamically inefficient. Professor William Rankine, designer of steam cycle theory, published calculations proving that 4-stroke operation wasted energy through unnecessary valve movements and incomplete combustion cycles. "This engine represents unnecessary complexity," he wrote in the Journal of Mechanical Engineering. Steam power has proven itself through decades of reliable service. Otto's four-stroke concept introduces failure points that will prevent commercial success. The Institution of Mechanical Engineers in London issued statements warning that internal combustion's unpredictable ignition timing made it unsuitable for industrial applications requiring consistent power delivery. Even some German manufacturers expressed doubts about abandoning proven steam technology for experimental engines that had never operated reliably in factory conditions. At 43 years old, Otto controlled Deutz AG through technical innovation and stubborn refusal to accept steam power's limitations. His engineers had built dozens of atmospheric engines across Germany's industrial regions, each one demonstrating that gas combustion could generate power more economically than coal-fired steam when properly controlled. Otto understood combustion physics intuitively after years of studying flame propagation and pressure dynamics, but four-stroke operation remained unproven at commercial scale. The compression stroke required precision machining that few German workshops had mastered, creating pressures that could destroy cylinders if materials weren't manufactured to exact specifications. Achieving reliable ignition at the precise moment when compression reached maximum demanded timing mechanisms more accurate than any mechanical device then in common use. Miss the ignition point by even a few degrees of crankshaft rotation, and the engine would misfire, wasting fuel and delivering erratic power that made industrial applications impossible. Otto faced a decision that would determine his company's survival and Germany's mechanical future. Developing a reliable four-stroke engine would require manufacturing precision that exceeded current German capabilities and testing programs that could bankrupt his company before producing marketable products. But if the engine succeeded, Germany could break free from dependence on British steam technology and establish mechanical engineering leadership that would transform the nation's industrial capacity. No major four-stroke engine had ever operated reliably in commercial service, and Otto's first attempt would be scrutinized by engineers worldwide looking for confirmation that internal combustion was a dead end. The chemistry of fuel-air combustion remained poorly understood, even by experienced gas engine builders. Some mixtures ignited smoothly, delivering steady power throughout the combustion cycle. Other mixtures with seemingly identical compositions detonated violently, creating shock waves that damaged engine components and produced noise that made sustained operation intolerable. Winter of 1876 brought Otto face to face with the magnitude of his commitment. He assembled Germany's most skilled machinists at the Deutz factory, explaining that success required manufacturing tolerances that exceeded anything attempted in mechanical engineering. The cylinders must be machined to dimensional accuracy within thousandths of an inch, preventing gas leakage that would reduce compression and waste fuel. Piston rings needed spring tension sufficient to seal against cylinder walls during compression, while allowing smooth movement that minimized friction losses. Valve mechanisms required timing precision that matched combustion requirements throughout wide-speed ranges. Otto's chief engineer Gottlieb Daimler arrived from Stuttgart with mechanical design credentials that commanded respect throughout German industry. The brilliant engineer had studied British steam technology extensively, identifying inefficiencies that internal combustion could eliminate through superior thermodynamic principles. His four-stroke engine design incorporated improvements that steam engineers had never considered possible. The compression ratio concentrated fuel energy into smaller volumes, increasing thermal efficiency beyond anything steam cycles could achieve. Precise valve timing controlled gas flow with accuracy that eliminated the continuous heat losses that made steam engines inefficient. Most revolutionary of all, Daimler designed the engine for portability. Unlike steam engines requiring permanent installation with boiler rooms, coal storage, and water supplies, Otto's four-stroke engine could operate anywhere fuel was available. The implications for transportation and mobile power applications seemed obvious to Daimler, even if industrial customers remained skeptical. The philosophy of precision manufacturing emerged from Otto's understanding that four-stroke operation demanded component reliability that steam engines never required. Steam power tolerated loose tolerances because external combustion processes never exposed engine internals to explosion forces. Internal combustion subjected every component to repetitive stress cycles that would destroy imprecisely manufactured parts within hours of operation. Otto's production crews developed machining techniques that created dimensional consistency across all engine components. Cylinder boring achieved roundness specifications that eliminated pressure leakage. Crankshaft grinding produced bearing surfaces smooth enough to reduce friction losses that wasted power in conventional engines. Valve seat cutting created gas-tight seals that maintained compression throughout millions of operating cycles. Chemical analysis transformed combustion from unpredictable explosion to controlled power delivery through systematic study of fuel-air ratios. Otto hired university-trained chemists who understood that combustion efficiency depended on mixing precise fuel quantities with exact air volumes. Too much fuel created incomplete combustion that wasted energy and produced carbon deposits fouling engine internals. Too much air reduced power output and increased combustion temperatures that damaged cylinder components. The difference between efficient operation and mechanical destruction measured in ratios that required scientific understanding rather than craftsman intuition. Quality testing at Deutz exceeded British steam engine standards through systematic examination of every component rather than assembly line production of untested parts. Otto installed dynamometers capable of measuring power output under sustained loading conditions that revealed weaknesses before engines shipped to customers. British steam manufacturers tested engines briefly and assumed they would operate reliably based on proven designs replicated countless times. Otto's crews tested every four-stroke engine for extended periods, recording performance data that identified problems requiring correction before commercial delivery. Engines that failed testing were completely rebuilt rather than shipped, with reduced specifications or maintenance requirements that would damage the company's reputation. The economic results vindicated Otto's precision manufacturing strategy within months of commercial production. By late 1877, Deutz produced its first batch of four-stroke engines, each one meeting specifications that Otto had promised to skeptical customers. Production costs per horsepower reached figures substantially below steam engine equivalents when calculated over complete operational life cycles, including fuel consumption and maintenance requirements. Otto had proven that German engineering could produce superior power sources at lower total costs than British steam technology that relied on proven designs and massive manufacturing scale. But the ultimate test waited in factory installations where four-stroke engines must deliver reliable power under conditions no laboratory testing could replicate completely. Industrial customers who had invested in Otto's experimental technology would determine whether four-stroke principles could deliver the consistency that steam power had provided for generations. Every engine Otto's crews had tested would face operating conditions that stressed components in ways bench testing never revealed fully. Real-world operation would prove whether precision manufacturing and scientific combustion control could create reliability and power sources designed to replace steam engines serving German industry for decades. The first commercial installation of Otto's four-stroke engine occurred in a Cologne textile mill through November 1877, like a mechanical equation written in precision machined German steel. Each component positioned with accuracy that would determine whether internal combustion could achieve what steam engineers declared impossible for mobile power applications. The engine operated at 180 revolutions per minute, slower than atmospheric engines but faster than most steam installations while delivering 12 horsepower continuously throughout 8-hour factory shifts. Traditional steam engines for equivalent power required boiler rooms occupying 4 times the floor space that Otto's four-stroke engine needed, plus coal storage and water systems adding cost and complexity to factory layouts. The textile mill's owner, Heinrich Burgers, had risked his company's production capacity on Otto's untested technology specifically because steam engine operating costs were destroying profitability. Coal prices had increased 40% over 5 years, while British competition forced textile prices downward, creating margin pressures that demanded radical cost reduction. Burgers calculated that Otto's engine, if it operated reliably, would reduce power generation costs by 60% compared to his aging steam installation. But if the four-stroke engine failed during production runs, his mill would lose orders to competitors operating with proven steam technology. The installation process revealed the maintenance advantages of Otto's design philosophy through systematic comparison with steam engine. Requirements. The four-stroke engine required no boiler operators, no continuous coal feeding, no water treatment to prevent scale buildup destroying heating surfaces. Fuel consumption measured in precise quantities per hour rather than the variable coal usage that made steam engine operating costs unpredictable. Startup time dropped from the 45 minutes required to raise steam pressure to under 5 minutes for Otto's engine to reach operating temperature and stable power delivery. This responsiveness allowed the textile mill to match power generation precisely to production requirements rather than maintaining steam pressure continuously to avoid lengthy restart procedures. The mathematical calculations governing combustion efficiency required that every component operate within design parameters that left no margin for imprecise manufacturing or careless assembly. December through March 1878 witnessed the most comprehensive operational testing any engine had ever received as Burgers's textile mill ran Otto's four-stroke engine continuously under industrial loading conditions. Daily operation averaged 10 hours with power demands varying from 20% to full rated capacity as different textile machinery operated throughout production schedules. Engineering inspections conducted weekly detected no signs of mechanical wear, valve deterioration, or combustion chamber damage despite loading cycles that exceeded design specifications regularly. Fuel consumption remained consistent at 2 pounds of coal gas per horsepower hour, substantially below the 3 pounds of coal that steam engines required for equivalent power output. The performance data attracted attention from German manufacturers desperate to reduce energy costs, threatening their competitiveness against British imports. By summer 1878, Otto received orders for 47 engines from factory owners willing to risk unproven technology for potential operating cost reductions that could mean survival versus bankruptcy. Technical criticism from steam engine advocates intensified, as four-stroke engines demonstrated reliability that contradicted predictions of inevitable failure. The Engineering Times published editorials warning that internal combustion remained fundamentally unsuitable for industrial applications requiring sustained operation. No gas engine has operated long enough to demonstrate long-term durability, the newspaper declared. These motors represent dangerous experimentation with factory productivity, built on theories rather than the proven experience that steam power provides. Even some German technical schools referred to four-stroke engines as Otto's gambling machines, questioning whether compression ratios and combustion timing could maintain consistency throughout years of service that industrial power sources required. Professional engineering societies issued statements questioning the wisdom of internal combustion for critical manufacturing applications. The Institution of Mechanical Engineers in London published technical papers calculating that four-stroke valve mechanisms would wear rapidly under sustained operation, potentially causing catastrophic failure during production runs. British engineering schools taught that internal combustion required decades of testing before responsible engineers could recommend abandoning steam power for factory installations. French manufacturers refused to consider four-stroke specifications for any application where production reliability determined business survival. The completed engines stood as monuments to German precision manufacturing, their machined surfaces reflecting workshop light in ways that cast-iron steam engines never could achieve. Each engine carried not just mechanical components but Otto's reputation and Germany's hopes for technological independence from British industrial dominance. The mathematical calculations predicting combustion efficiency assumed material properties that Otto's quality control had delivered, but actual long-term performance would require years of observation to verify whether four-stroke engines could match steam power's demonstrated longevity spanning decades of factory service. Operations continued through seasonal temperature changes, testing thermal expansion calculations with conditions swinging from summer heat to winter cold. Otto's precision machine components contracted and expanded according to design predictions, maintaining compression ratios and valve timing while accommodating thermal stresses that would have caused inferior engines to seize or lose power through component misalignment. The consistency of manufacturing tolerances throughout each engine ensured uniform thermal behavior that prevented stress concentrations at bearing surfaces where varying expansion rates could cause rapid wear or catastrophic bearing failure requiring expensive repairs and production downtime that would justify steam engine advocates' skepticism about internal combustion reliability. Public confidence in four-stroke engines required demonstrations that could overcome decades of steam-powered dominance and institutional resistance to technological change. But testing engines designed for stationary industrial service presented challenges that dynamometer measurements could not address completely. Industrial power sources experienced variable loading from machinery startup surges, continuous operation at partial capacity, and emergency overload conditions that created stress patterns impossible to replicate through laboratory testing methods. Otto needed proof that would convince both technical experts and conservative factory owners that four-stroke engines could support their businesses reliably. The breakthrough demonstration occurred at the 1878 Paris Exposition when Otto's engine operated continuously for 6 months, powering exhibition machinery while consuming fuel quantities that astonished visiting engineers. Steam engines providing equivalent power would have required coal deliveries totaling 42 tons throughout the exhibition period. Otto's four-stroke engine consumed gas equivalent to 11 tons of coal, reducing fuel costs by nearly 75%, while occupying 1/4 the floor space that steam installations required. French engineers, who had dismissed internal combustion as theoretically interesting but practically worthless, examined Otto's engine with growing recognition that German innovation had achieved something fundamental. International adoption accelerated through 1880 as manufacturers across Europe and America recognized that four-stroke engines offered economic advantages that justified their higher initial costs compared to steam power. British factory owners, initially resistant to abandoning steam technology their nation had perfected, began installing Otto engines for applications where fuel economy and installation flexibility outweighed steam's proven reliability. By 1882, over 2,800 Otto four-stroke engines operated in factories worldwide, generating combined power exceeding 15,000 horsepower, while consuming fuel at rates that would have required 3 times as much coal if produced by steam engines. The economic impact became undeniable as industrial customers calculated total operating costs over multi-year periods. Otto's precision manufacturing philosophy created engines requiring minimal maintenance compared to steam installations demanding constant attention from boiler operators, firemen, and maintenance crews. Four-stroke engines operated for months between servicing intervals, reducing labor costs that represented substantial portions of steam power's total operating expenses. Technical performance data accumulated as increasing numbers of engines operated under diverse industrial conditions, providing comprehensive evidence that four-stroke principles delivered reliability matching or exceeding steam power. Monthly inspections detected wear patterns that allowed predictive maintenance, preventing unexpected failures that steam engines experienced regularly despite decades of design refinement. The consistency of Otto's manufacturing standards meant that replacement parts from any Deutz production batch fit any engine regardless of when manufactured, eliminating the custom fitting that steam engine repairs required when components from different suppliers or production runs failed to match precisely. Comparison with steam installations revealed the operational advantages of Otto's compression ignition philosophy and systematic quality control. Traditional steam engines showed efficiency degradation within 2 to 3 years of installation as boiler scale reduced heat transfer and mechanical wear decreased component precision. Four-stroke engines maintained fuel economy throughout years of service with combustion efficiency remaining within 5% of original specifications. Cost analysis demonstrated the economic benefits of superior fuel efficiency rather than accepting higher operating expenses with lower capital investment. The transformation of global transportation began its revolutionary phase in 1885, when Gottlieb Daimler, Otto's former chief engineer, adapted four-stroke principles to create the first practical gasoline engine. The lightweight motor weighed just 160 pounds while producing half a horsepower, making it suitable for installation in vehicles impossible to power with steam engines. Daimler's motorcycle, constructed that same year, demonstrated that Otto's combustion principles could propel transportation beyond railroad tracks and waterways that confined steam-powered mobility. The philosophical foundation remained identical to Otto's stationary engines: four-stroke cycle, compression ignition, precise fuel-air mixing, systematic quality control ensuring component reliability. Carl Benz followed within months with his three-wheeled automobile powered by a four-stroke engine, incorporating every principle Otto had proven through industrial applications. By 1890, Otto's once mocked four-stroke design had become the universal standard for internal combustion engines worldwide, powering not just factory machinery but the emerging automobile industry that would transform human civilization. The 1900s brought exponential expansion of four-stroke applications as inventors recognized that Otto's principles could scale from fractional horsepower motors to massive marine engines producing thousands of horsepower. Rudolf Diesel's compression ignition variation proved that four-stroke cycles could operate with even greater efficiency using different fuel types while maintaining Otto's fundamental combustion sequence. By 1910, steam power had become obsolete for most applications as four-stroke engines demonstrated superiority in fuel economy, installation flexibility, maintenance requirements, and power-to-weight ratios. The Industrial Revolution's second phase, powered by internal combustion rather than external combustion, accelerated technological progress beyond anything steam technology could have enabled. Aviation development depended entirely on four-stroke engines light enough for aircraft installation while delivering power sufficient for controlled flight. The Wright brothers' 1903 success required a custom-built four-stroke motor incorporating every principle Otto had established: compression cycle, precisely timed ignition, efficient combustion chamber design, quality manufacturing, ensuring reliability. Modern analysis reveals the economic and engineering consequences of Otto's quality-focused philosophy versus contemporary cost optimization approaches that prioritize immediate expense reduction over long-term performance. The original 1876 Otto engine, preserved at the Deutsches Museum in Munich, remains mechanically sound after 148 years, demonstrating manufacturing precision that created permanence rather than planned obsolescence. Contemporary internal combustion engines, despite computer-controlled fuel injection and materials science advances, typically require major rebuilding within 150,000 to 200,000 miles of operation. The performance degradation reflects manufacturing philosophies that accept shorter service life with lower initial costs rather than Otto's approach emphasizing component quality and precision assembly. As automotive manufacturers invest billions in electric vehicle development to replace internal combustion engines, the four-stroke motors powering current transportation still incorporate every fundamental principle that 1870s engineers mocked as impractical, overcomplicated, and unlikely to succeed commercially. Otto's achievement proved that revolutionary technology often appears absurd to experts committed to existing methods, that precision manufacturing creates value exceeding immediate cost calculations, and that systematic quality control produces reliability that outlasts predictions from authorities declaring innovation impossible. The engine that mechanical experts ridiculed in 1876 powered the 20th century's transportation revolution and continues operating in billions of vehicles worldwide, providing permanent testimony that German engineering excellence, supported by scientific principles and systematic manufacturing control, can create technology serving humanity for generations rather than decades.